22nd Colloquium today. It's my pleasure to introduce Jouko, who will be speaking about inner models from extended logics.
Thank you, and thank you for the invitation. So this is a joint work with Juliet and Menachem Aguilar, and I will give next week 3 more technical talks about this. So today is without technicalities. Okay, so the starting point is definition of L as given by Gödel. So, of course, this is familiar to all of you, but maybe it's good to say once again why Gödel defined this model. As I understand, he wanted a model for continuum hypothesis, and so he took with this transfinite induction on every level of the only those sets which are absolutely necessary to take. So those which are first order definable over what you already have, you have to, in a sense, you have to take, and if you make that decision, then it turns out that continuum hypothesis and axiom of choice are true. So it was a good choice, but it's in many senses it is the minimum model that you meaningfully can consider in set theory. Because if you already have this level L alpha, I mean, then why not take some first order definable subset as a set? I think no mathematician who understands that far this construction would say that you can't take accept as a set a definable subset of something you already have. Okay, so now there is an alternative definition by Jensen, which is actually what we will use when we go the technicalities, because it's easier to deal with. So I just mention it because it will then show up. So there, the definability is kind of broken into these so-called rudimentary functions, kind of primitive recursive set functions, rather than first order definability. But now we defined a new model, inner model. We slightly modify Gödel's L. As I said, Gödel's L is based on the idea that you have a set and that you accept as new sets definable subsets. Now we accept those which are definable in a logic L star. I will talk about these logics. So I will say what I mean by a logic, but why should it be only first order definable? Well, many things can be said in favor of first order definability, like absoluteness and so forth. But anyway, we take this challenge that we take subsets of the levels so far which are definable in a logic which extends first order. That's why the inner model is called inner model from extended logics. So then that means that in the next level, L prime alpha plus 1, a typical element is the set of elements of that level which satisfy a definition, which are defined. So which the set X, which is definable by formula phi with some parameters, and this phi is now not necessarily first order, but an extended first order formula. Okay. Now, if we so then we call the resulting hierarchy of constructive sets CL star. So this is the Gödel's hierarchy when we change personal logic to L star. And it's easy to see that it's always a model of CF. There is some trouble with axiom of choice, but okay, so I will explain it using this notion of adequacy to truth due to Pfefferman. Logic is adequate to truth in itself if the logic itself can define its own truth. Now, as everybody who is adversed in mathematical logic knows, truth is both definable and undefinable. Okay, so we have to live with that. So here is the definable part. We can define this formula SAT for the logic if it is adequate to truth in itself. There is this formula which defines what formula phi with Gödel number phi in this corner brackets says about some parameters in, for example, any admissible set. This is when you start studying or writing a book on L or something, there is this tedious part where you define the coding of the syntax and construction of L, and you have to do the coding in order to, for example, to get the well ordering. So you get this total well order of, and here if you use, instead of first logic, you use any logic L star, you also get if the logic is adequate to truth in itself. And now not every logic is adequate to truth in itself, so there is a sort of a problem there. It is not very well understood, but the logics that we usually think of are adequate to themselves, like okay. So then we get this well order of L prime alpha, but this formula which defines a well order is not a first order formula; it's a formula of the new logic. So here is some history. In a sense, this kind of approach that I explain here was started by Chang in Andrzej Moskowski's seminar in Warsaw in 1967, and he talked about the idea that what if in L we replace first order logic by an infinitary logic, and then he published it in Proceedings of Symposium for Applied Mathematics in 1971, which is some. So, and the model that you get from that is so-called Chang model. The same meeting, Myhill and Scott showed that if you take the second order logic, you get Horn. Then, few years later, Glöde investigated the possibility that you use other infinitary logics, including L kappa omega, and he observed that with L kappa omega you don't get anything new, you get just L. Then some time passed, 45 years passed, and we started it Kennedy, Magyar, and me as a completely general project. This is related to Juliet's project on formalism freeness. So the idea is to study how free is L of the formalism that you. Is there some kind of formalism free content in L? Is L somehow more like stable under variations of its definition, as it turns out to be? But then when we studied this phenomenon, then we sort of got, I think, carried away, and we forgot the original problem of L, because we got into models which were quite far from L. But anyway, the paper is, the first part is published in 21, then the paper by Philip Wells, Friedman, Gittler, Müller, and something similar, but not quite same. Uriar, the postdoc who wrote about it, and there's a square group in the American Institute of Mathematics working on this. Okay, so I said that L star is some extension of first order logic. Let's look at extensions of first order logic. I already mentioned these infinitary languages which inspired Chang, higher order logics which inspired Myhill Scott, and generalized quantifiers which inspired us. Okay. More exactly, this is a map of logics as I know it. So here are the infinitary languages, here are the so-called absolute logics, in fact strictly absolute logics. Here are the generalized quantifiers, and we will talk about this quantifier and this, this, also a little bit of this. And then there are the higher order quantifiers. What is curious is the intersection of this, is that the intersection of this absolute part and the countably compact part is a singleton first order logic, that's the so-called Lindström theorem. So in principle, you can take from this map any logic and construct L and ask yourself what model, inner model set theory we get if we do this. Here are some examples which I already a little bit mentioned. So first order logic, you get L itself, L omega 1 omega, you get L of R, which is a nowadays very well known inner model. L omega 1 is the Chang model, and L2 is hard. So in these cases, the result is sort of known already. But what about all these other logics? What will happen with them? Now, in order to well, if we think of the motivation why we study these inner models, this kind of inner models that come from this, it's not just opportunistic, frivolous curiosity that what happens if this, what happens is that if that. Although there is a little bit of that, of course, but on the other hand, it is important for set theory, for development of set theory, to come up with inner models which are, they are very important if we can come up with new inner models which have such attributes as forcing, the theory is forcing absolute, they support large cardinals, satisfy axiom of choice, arise naturally, quote unquote, and decide questions such as CH, which is related of course to the forcing absolutes. Now, if we look at the existing inner models in the literature, because L is forcing absolute but doesn't carry large cardinals above weakly compact. Pod has large cardinals but is forcing fragile. L of R is forcing absolute, has large cardinals but doesn't have axiom of choice. Then there are the extender models, very important models, which are tailor-made to support given large cardinals. So they are very nice. But how natural they are from the sort of a priori point of view when you don't particularly focus on certain large cardinals is another matter. Okay. Yes. Can you speak up for many reasons? Yeah, L doesn't change at all, but L does change. Yeah. Yes, to say Positive absolute is a little bit cutting corners. Yeah. But there is a certain strong forcing absoluteness phenomenon in LOR. So now let's go into the business. We modify L by changing first order logic to something which is an absolute logic in the sense that truth and sentencehood can be defined by a delta 1 formula with respect to CFC. Even with ordinal parameters or parameters from L, then it's very easy to see that the constructible hierarchy doesn't change. But it already follows from this simple observation that if you add any of these quantifiers Q alpha, so quantifier Q alpha says there are Aleph alpha many. So very much not first order quantifier, but it doesn't change L. So these quantifiers can be freely added to first order logic and you get the same L. What about Magyar-Mali's quantifier, which is a kind of a higher order, not higher order, but higher arity quantifier? So it says that of n variables that there is a set, subset of the universe of size at least Aleph alpha, so that any n tuple from the set satisfies phi. This is much stronger than this Q alpha, which just say that there are Aleph alpha elements. For example, you can express Suslinity over 3 with this this quantifier. And it can be axiomatized assuming diamond. But without diamond, it can also be very badly behaving. Consistently, this is different from L. But if we assume a little bit of large cardinal 0 sharp, then this still gives L. And okay, so this is maybe a little bit surprising that this, which in principle can be quite strong, it still doesn't extend L. And it would perhaps be more expected that if 0 sub exists, then this is different from L, but it actually collapses. And without 0 sub, it can be different from L because we can code, we can take Suslin trees and then kill them selectively. Okay, so now we move to something which really takes us away from L. And this is this so-called Koff model, inner model L star. In this inner model, the quantifier Q, the cofinality quantifier, is defined so that it quantifies over 2 variables, and it says that the formula phi of the language defines a linear order of cofinality omega. This is due to Sela. This is completely recursively axiomatizable. One can say very intuitive axioms such that, like, if 2 linear orders are sort of like cofinal in each other, then their cofinality is the same. And it's fully compact, which means that it is compact in any vocabulary, however big, in CFC. And it has downward Lerner's column theorem down to F1. Okay, so now let's denote by C star. From some accidental reason, it is called C star. So C star is a constructible hierarchy which you get when you extend first order logic by this fully compact logic, which has a cofinality quantifier. Now the situation is different. If zero sharp exists, then zero sharp is in this. So it's definitely different from L. I will go through these technical details in my lectures next week. But here, this is so simple that maybe I can say that if we take yes, so if we look at the ordinals below alpha omega, which are regular in L and have uncountable cofinality, it can be proved that if zero sub exists, then these are indiscernibles. They are in the set of indiscernibles for L, and it's an infinite set. So then we can define, because this is in C star, we can define zero sub by reference to any increasing sequence. So this is a this cofinality greater than omega here comes into use because when you have this indiscernibles for L, any element of L is obtained from indiscernibles by a term, and there are unaccountably many terms. So terms with the variables. So this uncountable cofinality comes. This has been extended. I'm not going into the extensions. Can you speak up?
Is the set of omega n's in C star?
What did he ask?
Is the set of alpha n's in C star?
Now, I don't know if this microphone can pick up what you are asking. I hear that you are talking, but I don't know what you are asking.
Is the set of all n's in C star?
Is a set of aleph n's in the set? First of all, aleph n, it's an infinite. Or the set of all aleph n's. Is it in C star? No. Oh yes. Okay. Now I understand the question. Any in C star, it is the set of yeah, I have never thought about that. That's in C star. There is a result later that if you have an infinite, if there are infinitely many measurable cardinals, then no infinite set of those is in C star. The aleph n's are not measurable. So it could very well be that it's assuming zero sharp, but it's not. But okay, don't know. But good question. So C star is actually closed under sharps. There's an error. There should be X sharp is in C star for X. So you can iterate the sharps and they are all in C star. The dot Jensen core model can be proved to be contained in C star. So it's a set of all dot Jensen mice. You prove by induction on the mouse order that they are all in C star. And the proof is more complicated than this, but essentially there is something similar. And then if one goes a little bit further, if L of mu exists, then C contains some L of mu. This is, we couldn't prove so far that L mu itself is contained in C star, but we get an iterate which is contained in C star. So now if this is an application of Scott's old theorem, which started in a sense the whole iterated ultrapower inner models business. If there's a measurable cardinal, then V is different from C star, because if you take the Scott embedding from V into M, M to kappa sequence sign M, then C star in M is the same as C star in V, because it's just about countable sequences when M is V, and this contradicts the Kuhnen's result that there is no embedding from V to V. So if V equals C star, then there are no measurable cardinals. But we don't know whether C star itself whether C star is different from V consistently and there's a measurable cardinal. There are inner models with measurable cardinals in C star, but we don't know whether they are in C star measurable. This is one of the main open problems about C star. Here is this what I referred to already, that if E is an infinite set of measurable cardinals, then it is not in C star. This is really a modification of Kuhnen's result that if there are uncountably many measurable cardinals, then C star, then the Chang model doesn't satisfy choice. It's the same elements of the proof. Now we go to applications of stationary tower. So the usual countable stationary tower gives an embedding from V to an inner model M of the generic extension, which is closed under omega sequences, and omega 1 is mapped as a critical point and is mapped to the Wooden cardinal. There's a modification of this, which I know from a paper I know from Makirov, but it is in a paper by Makirov and Forman on generalized on continuum hypothesis, and also in Forman's chapter in the Handbook of Set Theory. So if you have a bigger cardinal than omega 1 below the Wooden cardinal, then you can find a stationary tower, a different stationary tower, which preserves cofinality omega and maps kappa to lambda. So these two we use here. So for example, if there's a Wooden cardinal, then I mean I'm going to assume in almost every result that there's one or many Wooden cardinals, because otherwise these methods don't work, because we use stationary tower. But on the other hand, if there are no Wooden cardinals, on the other hand, one can start even from L and prove consistency results of all kinds. But we were in this project, we were more interested in this situation that we assume any large cardinals whatsoever, anything goes, proper class or measurable Wooden cardinals, whatever. And then what can we say about these inner models? That leaves open what happens if we are in some inner models with no very big large cardinals. So omega 1 is strongly Mahlo in C star. I will not go into it through the proof, but this kind of proof is rather standard using the stationary tower. And all other uncountable regular uncountable cardinals are weakly compact in C star. We don't know whether omega 1 is weakly compact, by the way. That's an open question. I sort of think that it probably is, but we couldn't prove. And also that if there's a proper class of Wooden cardinals, then the regular cardinals from Aleph2 onwards are indiscernible in C star. An application of sort of of the stationary tower, a forcing which allows us to move around these cardinals. Here's an interesting computation what C star is in a concrete situation. Suppose V equals L of mu. So we should understand this. This is a model that we should understand very well. What is C star then? Well, as it turns out, you iterate the model. It has a measurable cardinal, so you iterate it omega square times. So your measurable cardinal goes omega square times up, and then you take this the sequence of all these which previously were measurable in this iteration. So you go deep into this inner model, but then you add this kind of prickly sequence into the inner model, and that is exactly C star of V. So here we can actually compute C star. Of course, if V equals L, then C star is L, so there's nothing to do there. Now this is an important, even if it's not very complicated to prove using stationary tower forcing, that the theory of C star is independent of forcing. It's stable under forcing if we assume there's a proper class of wooden cardinal, so that after any forcing there is some wooden cardinal left. And this also shows that the theory of C star is independent of the cofinality. So there is nothing sacred or like smart in studying the omega cofinality quantifier. You could take any cofinality in any regular cardinal and you get the same theory.
Something about the universal bareness of the set of the model.
Do we know about universal bareness in C star? Can you ask a question?
So are the sets of real in C star universally bare?
It's a delta 1,3 set. But it's a countable set. The set of reals is a countable.
It's a countable set.
Yeah, because omega 1 is Mahlon.
The omega 1 Malo, not the wooden cardinal. Sorry.
Omega 1 is strongly inaccessible in C star. So the reals of C star is a countable set. It's lightweight delta 1,3.
C star over the reals, then we can ask if the set of reals are universally bare.
C star over the reals. Never thought about that. Yeah. But then you suggest that then you can ask what the reals is it universally bare?
I mean, sometimes this doesn't make sense. Because the reals are not well ordered, so I don't know if C star. I guess it could.
Okay, good question, but this C star over the reals is not something I have done. We will come in this talk to C star over one real, but that's a different thing. Okay. By the way, I think this is an early observation we made, one of the first, and it's kind of curious because everybody thinks that continuum is RF2 or RF1, and in this C star, the continuum is at most RF2, but we don't know which. In fact, we tend to think that it is probably this continuum hypothesis is true in C star, but we don't know. But this is an easy model theoretic argument because it is you have to construct a model of size RF1 which observes cofinalities. It is essentially a kind of a union of chain model theoretic argument. because C star doesn't have the kind of condensation that L has. But if we look at aleph, I mean aleph 1 of V is a huge cardinal, I mean big cardinal, inaccessible cardinal in C star. If we have so big cardinal, then we can do a kind of a condensation. So here is this thing what I said about C star with respect to real X. We were not able to prove continuum hypothesis of C in C star. That's still open. But if we take C star with respect to a real X, then by using Martin's Turing determinacy, then if there are enough Turing cardinals in order to get certain determinacy, measurable above them, to get some iteration, then there's a cone of reals, a Turing cone of reals, such that C star X satisfies the continuum hypothesis. This is very it's a result which doesn't bring a lot of satisfaction. Yes, because there is this burning question: what about continuum hypothesis in C star? And this really doesn't say it. But cone of reals is a cone of reals. It's a cones form a filter, so it sort of suggests that continuum hypothesis is true, but it's still open. We can, as I said, if we forget about large cardinals, we can using number forcing, modified number forcing, we can construct starting from L a model in which continuum is anything whatsoever, and even a model where V equals C star and continuum is aleph 2. It's at most aleph 2. So, and of course there is it's consistent that C star satisfies continuum hypothesis, because if V equals L, then C star is L and satisfies continuum hypothesis. But here is a model where continuum is aleph 2. It's all based on coding by number forcing. We use number forcing to modify the cofinality of aleph ends of L, and we just use this coding to okay. So now I go so I have like 20 minutes, 15 minutes.
Yeah, you have
20 minutes now. What's that? Okay, so
10 minutes a slide.
10 minutes.
You have 2 slides left, so 10 minutes a slide.
Oh. What happened to my slides? Well, let's see. So I go to the other model. So let's see what I have here. Okay, one slide. Okay, so this we look at this quantifier almost all S phi S is now a second order variable, and almost all S phi S says that if you look at the countable subsets of the universe and you ask whether they satisfy phi or not, then there is a club of countable subsets which satisfy phi. So this is quantifier also suggested more or less in this form by Sela, but in a different form by Mackay, Kaufman, and Barwise. and it has a nice axiomatization. It has Browner-Levenaz column, a kind of Browner-Levenaz column theorem. It's a very nice. It has, one could say, even a nice proof theory, although it hasn't been much pursued. So let's see what is a model if you replace first order logic in the definition of L by this, and we call it the AA model. And of course, C star is a subset of this AA model.
Maybe there are more slides. What if you push the button again?
Okay, so
Now we just don't know how long.
Yes.
We're going to be here for hours.
no.
What is a large project?
Okay, so now comes the problem, not only the bullets there, but that we, contrary to our first impressions, we couldn't prove cannot prove that the AA logic satisfies adequate to truth in itself. This difficulty was observed by Gabriel Goldberg and informed us. So we modify the definition of the new L, and while we do it, we also go to this Jensen hierarchy because it's easier to do. What happens is that in the original definition we change the concept of definability from first order formula to L star formula. Now what we do is we include in the definition of L the truth definition of L star, the whole truth definition, not just that always when you have to define something you can use L star. Now you can use the whole truth definition. For first order logic it doesn't matter because in L the truth definition is definable in the same with the cofinality logic. There you can define the truth because they are adequate to truth. But if the logic is not adequate to truth, then you simply have to throw in the truth definition. So here is the truth definition of L star. We code those pairs alpha such that the level alpha phi is true where phi is in this L star. And we do it in order to get reflection or condensation, we have to do it for all levels. So it doesn't help enough to know what accidentally happens to be on some level. You have to know also with respect to the lower levels. This is common in set theory. You have to build in reflection or condensation or something like this. So here is the truth definition. It's induction, so it refers to its earlier levels. And then we just take the rudimentary closure with this operation of the truth definition. So when we go to technicalities next week, we will use this definition. One can ask, is it as natural as the original? And of course it is not maybe so natural, but on the other hand, all we do here is add the truth definition of the logic that we use into the construction rather than adding it like bit by bit. And after we do this, then this model CAA, which you get in this way, satisfies axiom of choice because all this J hierarchy in such satisfy axiom of choice. It goes back to Jensen's original paper, but it raises the question whether the original CAA, which uses like sentence by sentence construction, whether that satisfies axiom of choice, and that we don't know. So it's possible that this CAA defined as was defined in the first page of this talk fails to satisfy axiom of choice, assuming some large cardinals, but we don't know. But if we fold in the truth definition of the AA quantifier, we get choice. And now the difference between folding in the truth definition and having definability sentence by sentence, it seems to me rather like a minute difference. It's a small difference. It's difficult to hit into it, and that's why we don't know it. Anyway, now a very important concept in the study of this inner model is club determinacy, which is like determinacy in Z case. So any first order structure M is said to be club determined if for any formula phi with parameters either there's a club satisfying the formula or there's a club satisfying the complement of the formula. And having a club is really it's a game quantifier. Two people play a game in which they pick omega elements, and then when you at the end of the game they have a countable set, and you ask whether that is phi satisfies that or not. So it's really like this ordinary game in set theory where you alternatively pick like size zeros and ones, and then you have a real. Here you pick elements from the model, and then you have an infinite countable set, and you ask whether that satisfies the formula or not. And then we say that the inner model satisfies club determinacy if for every formula phi and every level this game is determined. It sounds like it's a strong assumption, but on the other hand, we are ready to make strong assumptions which help to prove it. So in fact, it turns out that all you need is proper class of Wooding cardinals or PFA, then this model is club determined. Okay, I will skip the proof, but now from now on we can use club determinacy. Now the first application, if there's a proper class of Wooding cardinals or PFA, then the theory of, suppose there are proper class of Wooding cardinals, then the theory of this AA model is set forcing absolute, just like C star. We can do the same kind of proof here.
Does that model contain the real or not?
No.
No.
There's no reason why it contains a real. The reals of this model are all in M1. Countable set in M1. Okay, then if there is proper class of Wooding cardinals or PFA, then every regular uncountable cardinal of V is measurable in this CAA. So it's not like C star where we don't know whether there are measurable cardinals. Every uncountable cardinal of V is measurable in this inner model. Now the main kind of result that we have so far proved is that if we assume club determinacy, then this CAA satisfies continuum hypothesis. And the proof of this is based on the concept of a pre-mouse, which we call AA pre-mouse. And in this AA pre-mouse, it's like pre-mouse in inner model theory, except that there are no measures. But we instead we are dealing with this AA quantifier logic, and we replace the idea of measure by a theory in the AA logic, and we are in a sense constructing a model for the theory. But anyway, the way we do this pre-mouse is a pre-mouse as an ultra product of pre-mouse, which is a kind of a definable ultra product. It's not a really ultra product because it's not. We don't have an ultra filter. It's a kind of a definable ultra product, ultra power, and then we there's a concept of iteration, and we iterate Aleph1 of V times a mouse, and we get enough information to conclude CH. There is a more elaborate proof along the same lines by Goldberg and Steele and Magiro, if I remember correctly, which gives actually GCH. So that much is known about this. So if I compare this models like the AA model and the C star, of course it may be that it turns out that they are just iterates of some inner models with large cardinals. Well, let's see. So far hasn't happened. But what is special about these models that their starting point is completely free of any large cardinal assumptions. So these inner models you can always build the inner model. C star, all you need is a cofinality omega quantifier. For the AA model, all you need is this almost all quantifier, and you can always build this. And then, depending on your set theory, they have certain properties, and we are mostly interested, if assuming proper class of unicorns, whether they become something stable and recognizable. It is conceivable that even more results about the AA model follow if one uses even stronger assumptions than proper class of Wooden cardinals, because there are determinacy results which are very strong, like the so-called Chang plus model. If we have determinacy there, then some of these results, I think, follow from that, and maybe more. I mean, we can maybe extend this AA quantifier to a bit more powerful quantifier. That's future work. So now, final inner model HOD1. So, as you may remember from the beginning of the talk, Myhill and Scott showed that if you take secondary logic, then you get what was already known, Gerald, the hereditary ordinary definable sets. What if we don't take all of L2, but just sigma 1, 1? And this is interesting because if you take sigma 1, 2, then you get all of HOD. But if you take just sigma 1, 1 part of secondary logic, then we get what we call HOD1. And in fact, a lot of things are in HOD1. You can say cofinalities omega, you can compare cardinalities, you can talk about cardinals, you can talk about exponentiation of cardinals. And as we know, you can use this in coding, like when we prove that HOD is not is crossing fractal. So especially C star is in HOD1 contained, the Magidon-Malitz is contained, the Hertig quantifier, about which I didn't talk about yet. And of course, zero sharp is in HOD1. Okay, so, but here is our main result about HOD1. It is consistent relative to the consistency of infinitely many weakly compact cardinals that for some lambda, the weakly compact cardinals, the set of weakly compact cardinals below lambda is not in HOD1. Of course, it is in HOD. And in this model, in fact, HOD1 is just L. So we can separate HOD1 from HOD. We don't know whether you can separate in the presence of very large cardinals HOD1 from HOD. It's possible, conceivable, that assuming, I don't know, supercompact cardinals, something HOD1 is the same as HOD. but otherwise it's a interesting submodel of one. Okay, the further work has focused on a close investigation of the relationship between C star and CAA. One can say nowadays rather accurately what are the inner models for large cardinals in C star, and they are below measurable cardinal, measurable limit of measurable cardinals, and in AA where you have inner models with much higher measurable cardinals, and even there are results about strong cardinals. Here are some names of the people who are working on this, and I mention also the result of Magirer and Schindler that the reals of AA are in M1. It's a delta 1-3 countable delta 1 light phase delta 1. We don't know whether it is a kind of an initial segment of the reals of M1 or what is it, but there is no inner model with a Woodin cardinal in the AA model, so that's the limit, and that's why we are working on also extensions of AA to stronger game quantifiers, and I think that finally finishes my slides. Thank you.
Yeah, are there any questions?
For this model, you have not looked at what happens if you throw in also the reals. I mean, you have these models which are generically absolute, and if you throw in also the reals, you might get.
You throw in all reals.
Yes. Then would you get, for example, for CAA, would you get that it's contained in the Chang model? So that it sits between LFR and the Chang model?
Well, I have a two-part answer. First part is I have never thought about it. The second is related to the first part, but I don't know. But a comment, it's a very interesting question. Yes, there are so many open questions here that we have not thought about that, but of course it was also I think Grigor asked it, something like this before.
Interesting because if you're in the analysis of sets of reals in this inner model could be very simple, and maybe you can prove that they are universally bad and get much more universally bad that you can reach by other ways. If you want to prove, for example, that the sets of real in the Chang model are universally bad.
Mm-hmm. That's a nice question, but I really have not thought about that. I have struggled to get axial choice into this picture. I'm so happy to have axial choice. Then if I throw in other fields, but of course it is an important inner model. Yeah, I have to write it down and think about it.
Jan, you had a question?
Yeah, could you recall the definition of C star?
Of
C star.
C star.
Yes.
Mm-hmm.
Oh, or just this one.
I guess I have a question. Has it been ruled out that any of these models are iterates of mice?
No. But there is another inner model that I did not talk about, which is between C star and the AA model, something we call D star, which is C star, which is you add the cofinality quantifier and then you add the AA quantifier, but restricted to ordinals, so ordinal domains. Then we get this D star, and we can prove that D star is obtained from the smallest inner model containing measurable cardinal, which has a measure one set of measurable cardinals below it, by iterating the measurable cardinal away from the universe and then iterating all the measurable cardinals so that their cofinality in V is uncountable. Then you get this D star. So this D star is a kind of an iterator mouse, but it is between C star and AA model.
What is the result about some of these models have models that are extended?
What?
Some of these models have inner models
Yeah.
themselves that are
Yes.
extended.
Yes. It's a question of first priority. Who has been what kind of inner models with large cardinals, and what kind of sharps these or versions of sharp like sword or and grenade or whatever these models contain. But that of course is a different question from whether the model itself is obtained from these mice.
Quick question. Did you think about whether there is a natural logic that when you build from it, you just get a model which is closed under every UV set,
Closed under?
closed under every university bear set in the omega conjectures, omega logic. So there's a term relation for every UV set.
What does it mean for a model to be closed under?
You have like a term relation that correctly interprets all the university bear sets of the models closed under.
Mouse operation. It's like an operation. Yeah. In many cases, if not in every interesting case, it's possible to define an ad hoc logic, but that's unsatisfactory. Your question was a natural logic, and for example, we have an ad hoc version of the AA quantifier, which so that the model which it defines does not satisfy axiom of choice, but it's not the same as AA. It is a sort of opportunistically defined quantifier which has a kind of the features that violate axiom of choice. But to have a model and then define a natural quantifier or logic is more difficult, and therefore we have, in a sense, the opposite approach, that we start from a natural quantifier and then we try to see what it is that we get. Like here we take, here is the AA quantifier, here is a cofinality omega quantifier. This did nothing, and this was does nothing, assuming zero sharp. So we have dealt with all these the generally known. I mean, there aren't any really essentially any other. Well, there are some, but essentially these are the main logics
You can combine different ones together.
What's that?
Well, what Uri's doing.
Yes, in Helsinki, UER is and from Jerusalem did his doctorate is on combining different cofinality quantifiers, and also he has studied the phenomenon that if you take C star inside C star, it may very well be different from C star, and the same with A. You can these are possible, and he has done transfinite sequences of these inner models, and they are different. But we don't know whether path determinacy implies this. So, having proved that this is possible, the natural assumption is to assume path determinacy. Whether it then follows that is not known.
So with Young determinacy, you expect that it is that the equality does not hold, or that the equality holds?
What is more likely? It's I think it is more likely that it's different, but it should somehow decide. Path determinacy should decide such questions, but it's more likely that it will be going this. But it really shows how little we know that I cannot even confidently say which way I suggest it, because this is a weird thing that this star inside C star is different. Is it something which happens from large canons, or?
But can you get the infinite decreasing?
Yeah. Yes.
Well, data logic, you should maybe say something about the William value.
Yes. Daisuke Ikegami has a project and a paper coming out in which he does the same thing for the Boolean valued second order logic. So if you do it for second order logic, you get this very forcing fragile HOD. So that's kind of unsatisfactory, although interesting. But if you, instead of second order logic, you have so-called Boolean valued second order logic, about which I have written a paper with Ikegami, then you get a forcing stable model, which is very big. But I don't want to advertise it too much because it's he's writing his paper. It's up to him to tell what the result.
There's an implication with the.
Yes, this is there is this Woodin's capital omega logic, which, by the way, is not a logic, strictly speaking. It's, you couldn't put Woodin's omega logic here, because Woodin's omega logic is just a set of rules, a kind of a rule of logical consequence in set theory. But there is a logic which you can put into this picture, and we call it, with Ikegami, we call it Boolean valued secondary logic, and it turns out that it is surprisingly close to Woodin's capital omega logic. But you cannot put equality because they just, as in spirit, let's say, it's like this symbiosis that Juliet talked about yesterday or the other day, 2 days ago, that you try to symbiosis tries to find equality between two things which come from different worlds, but symbiosis is what binds them. And I think this Boolean valued secondary logic and Woodin's capital omega logic, somehow they come from different worlds, but they are somehow symbiotic.
You know how the set of validities in the logics compare?
Which logic?
So Wooden's omega logic on the one hand, and then the Boolean second order.
The Boolean valued secondary logic, it's unfortunately not much less. For secondary logic, the validity is pi 2 complete, and for assuming large cardinals for Boolean valued secondary logic, I think it is delta 2. So it's a little bit better than for secondary logic, but I think that depended on some hypothesis on iteration hypothesis.
We continue the discussion.
Oh yeah.
Because restaurants in Gdańsk close at 10 o'clock. If you want to go to dinner later on.
All right. So let's thank Jouko again.
Thank you.